All right, today we are diving into the electric dipole, a tiny little thing that's all about twist and pull. We're going to see how these little pairs of charges act in electric fields, and it turns out their behavior explains some really cool stuff you see in the everyday world.
You know that classic science experiment, right? You run a comb through your hair, charge it up, and suddenly it can pick up little scraps of paper. But wait a minute, the paper isn't charged, it's neutral. So how in the world does that work? Well, physics has this incredibly elegant answer, and that's exactly what we're going to unpack together.
So here's the game plan. We'll start with the basics, putting the dipole in a nice, neat field. Then we'll get into the twist, literally, the torque. We'll see what happens when things get a little messy with the field, and then boom, we'll solve that comb mystery for good. Ready? Let's meet our main characters.
Okay, first things first, let's define our key players here. The electric dipole itself and the environment it's going to be living in, the electric field.
So what exactly is an electric dipole? It's actually super simple. Just picture a pair of charges. You've got a positive one plus Q and a negative one minus Q. They have the exact same strength, just opposite signs. And they're separated by some tiny little distance. That's it. That little duo right there is our electric dipole, and it's a huge deal in electromagnetism.
Now for the playground our dipole is going to be in, we're going to start in a perfect, almost boringly perfect world. A uniform electric field. You can just imagine a whole bunch of arrows, all pointing in the exact same direction, all with the exact same strength. It's like a perfectly steady river current. No matter where you are in it, the push is exactly the same.
Okay, let's do it. Let's drop our dipole into this perfectly uniform field. Now your first guess might be that the whole thing just gets pushed along, right? Kind of swept away by the current. But that's not what happens. Something way more interesting is about to go down.
So, take a look here. Our dipole is sitting in that field. Now the field is going to push on the positive charge, trying to move it in the same direction as the field lines. But for the negative charge, it does the opposite. It pulls it backwards against the field. So right off the bat, you can see this little tug-of-war going on.
And here is where things get really interesting. The strength of that push or pull is just the charge, Q, times the field strength, E. But remember, we're in a uniform field. That means E is the same everywhere. So the forward push on the positive charge is exactly equal to the backward pull on the negative charge. They perfectly cancel each other out. The net force? It's zero. Zilch, nada.
So, wait a minute. If the total force is zero, doesn't that mean nothing happens? The dipole shouldn't move from its spot at all. So does it just sit there? Well, not exactly.
See, the key is where those forces are acting. They're not pushing on the same spot, they're on opposite ends of the dipole. Think about using a wrench on a bolt. You push on one side of the handle and pull on the other. The net force on the bolt might be zero, but it sure is turning. That turning force is what physics calls a torque. So the dipole doesn't get pushed, it gets twisted. Okay, so how much torque are we talking about? Well, the formula for torque is basically the force times the lever arm, the perpendicular distance between the forces. We know the force on each end is Q times E. Now for that distance, if you look at the geometry, you'll see it depends on the angle the dipole makes with the field. With a little bit of trig, we find that distance is the dipole length, we'll call it 2a, times the sine of the angle, theta. So you multiply it all together. Torque equals force, QE, times distance, 2a sine theta. Now we can shuffle that around a bit. Let's group together the charge Q and the length 2a. This little package, Q times 2a, is so important it gets its own name, the dipole moment, and we give it the letter P. And just like that, our formula cleans up beautifully to the torque equals P times E times sine of theta.
And if you want to get really elegant about it, in vector form, it's even simpler. It's just tau equals P cross E. The torque is the cross product of the dipole moment and the electric field. It's just beautiful. This one little equation tells you everything you need to know, not just how strong the twist is, but which way it's twisting.
Okay, let's plug in some numbers to see how this works. Let's say our dipole moment P is 2 times 10 to the minus 12 coulometers. The field E is 10 to the 5 newtons per coulomb, and our angle is a nice, easy 30 degrees. We just use our formula. Torque equals P times E times sine theta. Well, the sine of 30 degrees is just a half, 0.5. So we multiply it all out, and we get a torque of 1 times 10 to the minus 7 newton meters. Pretty straightforward, right?
All right, so that's the whole story in a perfect, uniform field. But let's be real, the world isn't usually that neat and tidy. So what happens when we change the rules of the game? What if the field isn't uniform?
Well, our source material says it best. When the field isn't uniform, the net force is no longer zero. And that is a huge deal. That one little rule we built everything on, that the forces cancel out, is suddenly broken. And if the net force isn't zero, that means our dipole isn't just going to rotate anymore, it's going to move.
Okay, check out this diagram. See how the field lines are spreading out? That's our clue that the field is getting weaker as you go from left to right. Now, in that top picture, look at where the charges are. The negative charge is on the left, where the field is strong. The positive charge is on the right, where it's weaker. This means the backward pull on the negative charge is now stronger than the forward push on the positive one. The tug of war is unbalanced. The whole dipole gets a net pull to the left, towards the stronger field. And if we flip it around like in the bottom picture, the same logic applies. It'll be pulled to the right.
So let's just put it side by side. Uniform field, net force is zero. The dipole only twists. Non-uniform field, net force is not zero. It twists and it moves. It's really that simple. Whether the field is uniform or not is the absolute game changer here.
Okay, we've got all the physics we need. A dipole in a non-uniform field gets pulled. Now, let's go all the way back to the beginning. It's time to solve the mystery of the comb and the paper.
So here's the solution, step by step. 1. A charged comb does not create a uniform field. Not even close. It's super strong right next to the comb and gets weaker really fast as you move away. It is textbook non-uniform. 2. You bring that field near a neutral piece of paper. The field actually stretches the atoms in the paper, creating tiny, temporary dipoles right there inside. And 3, now you have these little induced dipoles sitting in a non-uniform field. And we know exactly what that means, right? They experience a net force. The end of the dipole closer to the comb gets pulled harder than the end further away gets pushed. The result? The paper is literally pulled towards the comb. Mystery solved.
And there you have it. We went from a simple magic trick with the comb all the way to some pretty fundamental physics. Let's just quickly recap the key takeaways from all this.
This table really nails it down. Case 1, a dipole in a uniform field. What you need to remember? The net force is zero, but it experiences a torque, that twist we talked about, given by tau equals P cross E. Case 2, a dipole in a non-uniform field. The big deal here? The net force is not zero. The dipole gets pulled, and our real-world example is that comb picking up paper. Simple as that. And I just want to leave you with this final thought. This whole thing, this twist and pull on dipoles, it's not just some neat classroom trick. It is everywhere. It's how your microwave heats up your food, by twisting water molecules, which are natural dipoles. It's fundamental to chemistry, to how molecules hold together. So the next time you see something stick together when it seems like it shouldn't, you have to wonder, could there be a tiny tale of twist and pull happening right there? Thanks for joining me.